So let's put a big box around these formulas. They're on your reference sheet. Have your reference sheet beside you while you're completing today's exercise, and let's start to get familiar with using these. Now, we're going to use them to find definite and indefinite integrals. It means that we can now also find areas, and in fact we'll be finding areas under curves that have formulas that look something like this. And we'll also be able to find a function given its derivative if we have a clue. So, a few examples here. In this first one, we need to integrate. Now, let's have a look at the basic form. We've got no square root and we've got the plus in the denominator, so it looks a lot like this one, where I can see that a is going to be 1, and if f dash x is e to the x, and f of x squared is e to the 2x, what we need to think through is the fact that e to the power of 2x is actually e to the x, all squared. And so we know that our little function of x here must be e to the x, because f dash x is also the exact same thing. So I can do that thinking on the side if I need to, or in your head once you get more familiar with it, and I can see that what I need here is 1 over a, well 1 over 1 will just be 1, so I don't really need to write that, and then I've got the inverse tan of my function of x over 1, so I've got e to the power of x over 1, I don't really need to write that, plus c. So that one was quite straightforward. Okay, the next one, it looks like we have this other form, so we're going for inverse sine of something. Now, 1 minus our function all squared, well I know that x squared gives me x to the 4, so if my function of x is x squared, it makes sense that f dash x, which is what I'm hoping is on the top if it's a perfect question, should be 2x, differentiating there. Now this is handy working to do on the side, because here what I've found is that this is not a perfect question. So I'm going to start by rewriting it as a perfect question. If I had 2x on the top and 1 minus x squared squared, which I've got x to the 4 there, then I know exactly what to do. But I don't have a 2. I've gone and multiplied by 2. I can make up for that by putting a half out the front. So then my half comes along for the right, and now I can say I've got the inverse sine of my function of x, which is x squared, over a, where a is 1, so I just have x squared in there, plus c. This last example says if a curve has a particular derivative and it passes through a known point, that's our clue, find its equation. Okay, so we want to start by saying, all right, we want to integrate 1 over 36 minus x squared with respect to x. And when we do that, what do we get? Well, it looks like this form here, where a is 6, and our function of x is just x. So if our function of x is just x, then obviously f dash x is just 1, and that's exactly what we've got. So it is a perfect question in that way, and it's a very simple integral to solve here. We've got the inverse sine of x over 6 plus c. So what we've found here, this is our equation now for y, because if the derivative dy dx had this equation, then y will be the integral of that. Now we need the clue so that we can figure out what the constant is. So now we want to sub in and say when x equals 3, y equals pi on 6. Therefore, and I'm sort of running out of space here, so I'll just work across. Therefore, pi over 6, which is y, is equal to the inverse sine of 3 over 6, which is a half, plus c. Now the inverse sine of a half, you can type it into your calculator, but it's probably easier to say, hey, this means the sine of some angle is a half. I know the sine of 30 degrees is a half, and 30 degrees is pi over 6. So here we have pi over 6 is equal to pi over 6 plus c, therefore c equals 0. So if c equals 0, then we already have our nice version of y here, and we've got 0 on the end, so we can say y is equal to the inverse sine of x over 6. And the answer in the end was quite simple. And now for a much trickier example, we need to differentiate x inverse sine x, and hence find the primitive of inverse sine x. Now remember, we've just learnt how to integrate where the result is an inverse trig function. We haven't actually learnt how to integrate an inverse trig function. So you'll never be expected to do that unless you're led into it with a question that explains what to do first. So this is a good example of one of those sorts of questions. After that, we need to find the area underneath this curve between x equals 0 and 1. So let's just start by following instructions here. Let's let y equal x inverse sine of x. And now we can differentiate that. Now we're going to need to use the product rule because we've got two functions of x multiplied by each other. So if you like to write your ingredients out, go ahead. U equals x, u dash equals 1, v equals inverse sine of x. So v dash is going to be 1 over the square root of 1 minus x squared. So now when we go to find dy dx, we have v u dash plus u v dash, and multiplying these together, I can literally just put the x on the top of that fraction. And I get this. Okay, how are we going to use that result? Well, hence we need to find the primitive of this. Now, remember that if you've differentiated something and you get some result, when you integrate that result, you'll get back to where you started. So I don't know how to integrate this, but I do know how to integrate all of this. So that's my starting point. Do what you can, see where it leads you. So I'm going to say if I integrate all of this, okay, then what I'm going to get is that. So let's just write it out. We have the result, so let's use it. And then we can get the part on its own that we actually want. Now, when I integrate something that's got two terms and they're added together, I can integrate them one term at a time. So if you like, I could almost have written this as plus, hang on, let's put a little dx in there, and then plus, and then integrate this with respect to x. That way you can really see it as two separate integrals now, even though in the beginning I was integrating it as one big thing. So on the next line, we can get the part that we want on its own by just leaving it on that side of the equation and subtracting what we don't want from both sides of the equation. So we'll get this part minus this part. Now, a word of caution, when you spot that, it's really easy to jump to conclusions and say, hey, that's inverse sine x. Is it though? If what we had on the bottom here was 1 minus the function of x squared, then the function of x in this case would be x, wouldn't it? And so what would you get for f dash x, which is what by rights should be on the top? You'd get 1. And we don't have a 1 there, we've got an x. So we actually can't integrate this using the methods that we've learnt today of integrating and getting inverse trig results. So what can we do? Well, we need to refer to our basic integration skills that we learnt in our integration chapter from the advanced course. And we need to now rewrite this a little bit differently. Now, we can see that what's on the bottom here is a function of x, and it's all inside a square root bracket. So what we could do now is we could just adjust the look of that and say, all right, we've got x multiplied by 1 minus x squared to the negative half. The half is the square root part, and the negative index is what puts it all down there in the denominator. And now we have this. Okay, now the rule that I'm going to remind you of, let's grab a red, write this on the side. If we're integrating some function that is raised to a power like this, and this is on the very top of your formula sheet for integrals, just a reminder, what we do is we say, hey, the perfect question has f dash x out the front, and then it has f of x raised to some power. And what we do with that, we just follow the instructions on the reference sheet, is we just take that function of x, we raise it to a power 1 bigger, we divide by the new power, and we add a constant. So this is a rule that we have here. Now, have we got the right powers of x out the front here? Is this indeed f dash x? Well, we've got f of x raised to a power, we'll call n minus a half, but here, f of x is 1 minus x squared. Now, what would f dash x be? If we differentiate that, we get negative 2x, don't we? So this isn't quite a perfect question. We can make it a perfect question though. The perfect question would have negative 2x out the front, because now it's sitting in this form, and we'll know exactly what the answer is. Now, I can't go and multiply something by -2. It's now changed it, unless I multiply by 1 over -2 or multiply by -half, and that's going to change the sign there. So what I did is I multiplied this by -2, but I also put half out the front, that'll cancel the 2, and I changed this sign. So I just adjusted this part to be a perfect question so that then I know what this integral is actually going to be. So the first part is still x, inverse sine of x, plus a half, that has to come along for the ride, and then when I integrate something in this form, f dash x times f of x raised to a power n, what I get is that function of x, so I get the 1 minus x squared part. I raise it to a power 1 bigger, so instead of minus a half, I need a half, okay? And then I divide by the new power, and the new power is a half, and I add a constant. Now we need to do a little bit of tidying up here. We've got a half and we've got a half, so they can cancel out. And if I want to, I can write this power of half here just as a square root. That might look a little bit simpler, okay? So now I've got my, my primitive of the inverse sine of x. Now, if I'm using it to find an area, then I'm not going to need the plus c. So while I'm integrating here, this was an indefinite integral, it would be correct to leave the plus c on. And of course, your final answer, you could tidy up and take those halves out of the way so that it looks neat. So to do part B, I'm going to leave this here because this is the part that I'm going to need. And let's rub off some of our working at the top here so that we can use it. So the area we're looking for is going to be the integral of sine x from 0 up to 1. And we've found that what will need to go in our square brackets then is all of this. It's fairly long and complicated, but we can get it done. From 1 to 0. So now I don't need that anymore. Now I can sub in 1 and then subtract in brackets the subbing in of 0. So subbing 1 in here, I've got 1 times the inverse sine of 1 plus 1 minus 1. Well, this part will all be 0, won't it? Minus, bracket, 0 times anything is 0, so that first term will be 0, plus, if I sub a 0 in here, I'll have the square root of 1, which is just 1. So the inverse sine of 1, that means the sine of what angle is 1. To do that, I just think about the sine curve. I know that the sine of pi on 2 gives me 1. So here I've got one lot of pi on 2, plus 0, I can get rid of that. And here I have minus 1. Careful not to make a classic sign error. So I've got pi on 2 minus 1, units squared, which you can write units squared or just u squared, either way.